So let's start from the first section. Uh, okay, we can find from here. Actually, the first one is related body. And third section, that talk about differential equations of motion of the body, including rotation around the fixed axis and plane motion. The final one is the principle of dynamics and its application. So I think we should finish the learning of first three sections. Then we'll go back to chapter 11. After we finish chapter 11's learning, we will back to here, talk about general principle of dynamics and its application, because this section will use all the principles we have learned. Actually, in this kinematic part, we have learned three principles. Now, chapter 13, we are learning the second principle of angular momentum. And when we back to chapter 11, we'll talk about the principle of work and force, 功能原理, work and energy. So let's start from this textbook. After our class, you guys can read by yourself. So the first one, we talk about the principle of angular momentum for a particle. So first, we should know what is angular momentum. Do you guys know this Chinese character? Actually, angular momentum, we call that 动量距. So momentum actually 动量. Now, do you remember we have this concept because we use P to denote momentum, and it's equal m times absolute velocity v, right? So that is momentum. Here, as in chapter 13, we are talking about angular momentum. So in some cases, maybe we also have another name in Chinese is 角动量. You know, angular means 角动量. But in many cases, actually, we always call that 动量距. So it's more like a moment for force to some point. Our moment also is a vector, the direction according to the direction of absolute velocity, right? So this vector also have a moment to some point or some axis. So its concept is a little bit like what we have learned, moment of a force to a point or to an axis from the first part, statics of our course this semester, right? So let's see. First, we are going to talk about angular momentum of a particle. So please, you guys can try to look at this picture. So this picture showed particle A of mass m moving along a curved space. So maybe this curve is its trajectory, right? So the particle located by its not opposition, I think, is position vector, because we have this fixed Cartesian coordinate system, right? So this original point O, when we link O and A, we use this OA denotes this point, this particle A is position vector R, right? So this position vector R with respect to a convenient origin point O of a fixed coordinates O, X, Y, Z. The velocity of the particle V equal R dot, that is dr dt. We have learned this, right? And its linear momentum is what we have learned from chapter, I think, chapter 12. So we have P equal mv. Maybe I can write for you guys once again. Maybe actually we have this concept P. When I use this PDF file, it's very hard for me to write something because my writing tool cannot use on this Acrobat or this PDF document. So it's hard for me to write something. So mv. So that means the momentum, linear momentum, just to compare to this so-called angular momentum. So P equal m times v, right? So its direction totally according to the direction of v. Here you guys always should pay attention to that v always will be the absolute velocity. So the moment of linear momentum vector mv about the origin O is defined as the angular momentum of particle A about point O, and it's given the cross product relation for the moment of vector. So do you guys still remember, actually we have to learn if we have a space, a force in space, right? We have to learn this if we have a force F in space. So we try to figure out if the moment to point O, we have this is a position vector cross product F. You know, that's what we have learned, a moment for a force to a point. So we can compare to this. Today we're talking about angular momentum. It's more like we use this mv linear momentum as a vector, and we calculate its moment to the same point, just like a space force, a force in space to the same point O. So that is angular momentum. We call that 动量距 or 角动量. So the angular momentum then is a vector perpendicular to the plane defined by R and V. These are two vectors. Actually, this is mathematical knowledge point, right? The sense of M0 is clearly defined by right-hand rule for cross product. So we should pay attention to the sequence of this cross product, because we cannot, it's not equal to when we change the sequence. If we try to use like mv cross product R, it's not the same thing, because when we use our right hand rule, you know, so first we should let our 4 fingers of our right hand to along the direction of R. Then you try to fold your 4 fingers. Let the 4 fingers this time will along the direction of mv. Then our thumb will point to a direction. So that direction will be the direction of m0 mv. So actually, if I link this point to O, actually we will have a plane, right? We will have a plane like this. So our new vector MOMV is, is determined from the cross product R cross product MV. Actually, this direction of this vector will perpendicular to this plane. No? And the magnitude of this will equal things, this not the thing. So I will erase this part. So when we are trying to find it magnitudes, that is MO. MV. Because here is the cross product, so we just need the norm of R vector and the norm of MV vector, and the sine angle. Let me see theta. Actually, this theta, or maybe I should use the same angle with alpha. No, because here we just draw another picture picture let you get find actual R vector have a intersecting angle of this vector MV. So its magnitude will just the magnitude of R times the magnitude of MV and times sine alpha. So if you look this picture, you will find actually this value will be 2 times area of S triangle OA. Let's see, this is B. Okay, so OAB. That's how we find, how we give the definition of momentum and how to do calculation to find the magnitude and direction. So this is the new concept of angular moment of a particle. So you guess very its logic path. When we finish this learning of a particle, we will try to move into a system of particles, right? So first we should know its concept. And the scalar components of angular momentum may be obtained from the expansion. So actually we can use R equal xi yj zk. So x, y, z actually is the components of R vector along x axis, y axis, and z axis. Because this mass will never change at any time moment. So we just have the absolute velocity v, its 3 components along x, y, and z. We use vx, vy, and vz to denote this. So I think this will very hard for you guys to remember, right? Maybe you guys will find it very difficult to remember this so long expression. So in my opinion, we do not need to remember this. You should remember the rules how to find this. So this is the determination calculation, right? So we actually, you can follow me. I never remember this long expression, and I think I cannot remember that very clearly and correctly. So I always remember the rule how to do this calculation. So please, you guys follow me. When we try to find mx, we just need to think about, we cut the first row and we cut the first column. Then we have a determine calculation. So actually this one you can find from this sub one is just equal y with z, because we also have m. So this is y times m with z minus z m v y, right? So you just, because you want to get the first opponent, so you should cut the first row, and the first column. Next time when you try to find the second one, my, so this time we cut the first row and then we cut the middle column, right? And this time, please remember, we have this determination calculation, determined calculation, but this time we should change the sequence. So that means we should use ZMVX to be positive, and the minus minus what? And here it wrong. It's not Z, it should be X. So that means for the middle one, we just need to find this X, Z, and Vx, Vz, right? But this time we should use this Z times MVX minus X MVZ. So here, not Z, should be X. And the third one, we use the same method. So for the third one, let me do some erase. Okay. Sorry. So for the third one, we use the same method, but this time we should cut the first row and we cut the third column. Then we just need to calculate this determinant calculation. So the third one will be x mvy, you see, and minus y mvx. So here another error. So if you guys have your textbook PDF, remember you should turn to this page 224 and change this expression. So actually, if you can remember, just I tell you how to do the calculation. We don't remember we don't need to remember this, because in any time we want to have some component, we can do this. So that is MO will equal MX I plus MYG. It's hard for me to write something on the screen, so it's very ugly. So please, you guys, you should know what I'm trying to write for you guys. So this is G. And I wonder if all you guys still have the impression we have learned the relationship between the same force. The same force in space is moment to a point, and it's moment to three axes, which a origin point also is the same point. So that means the three components of a force to the point O, M, O, F actually is the three moment of this the same force to x-axis, y-axis, and z-axis. That's what we have learned before. So that characteristic is still applied here. So that means actually the first component of this MO actually is the linear momentum. It's angular momentum to x-axis, and my means the linear momentum PV is angular momentum to y-axis, and mv, the third component, means the same PV is angular momentum to the z-axis. So each of these expressions for angular momentum, may be checked easily from figure 31, which shows the three linear momentum components by taking the moments of these three components about the respective axes. That's what I just said, right? And to help visualize angular momentum, we have this, and we know how to find magnitude, right? So the motion is viewed in the plane defined by r and v. The magnitude of the moment of mv about O is simply linear momentum mv times the moment arm r sine alpha or mv r sine alpha, which is the magnitude of cross product mo equal r cross product mv, right? So the final paragraph is tell us angular momentum is the moment of linear momentum, right? Here, linear momentum is P equal M times V, and must not be confused with linear momentum, right? So angular momentum is more like a moment for a linear momentum to a point. So from the international system units, its angular momentum has the unit kilogram meter squared per second. So please, we have given the important concept. What is angular momentum of a particle, right? What is the angular momentum of a particle, and how to do its calculation? We should review this method, how to do 3 times 3 rows, 3 columns is determine calculation. And the second the principle of angular momentum for a particle. So the topic of this chapter 13, we are talk about principle of angular momentum. But our logical path is from a particle to a lot of particles. That means a system of particles. Then we'll talk about some raised body which have different kind of motion types, maybe translational moment, maybe rotation around fixed axis, or maybe plane motion, right? So that is its logical path. So from the first section, after we gave the concept of angular momentum of particle, we move to tell us what is the principle of angular momentum for a particle. So let's see. The differential of angular momentum of the particle in 13 to 1 is here. Is here, 13 to 1, right? 13 to 1. Try to do the derivative calculation. Because we have R cross product MV, we try to do this. So dMOMV dt, that is the same thing, dr cross product MV dt. So from the mathematical calculation rule, we have, so first we keep R never change cross product dMV dt, right? And then we plus another, we keep the MV never change, and this time we do the dr dt. So this dr cross product MV dt will change into two parts. So let's talk about the first part. Actually, dMV dt is m dv dt because m never changed. So dv dt actually is the acceleration. You see, what is this? Actually, this is second law of Newton's, right? It is second law of Newton's, and actually this is what we have the principle of momentum from chapter 11. We just finished the learning, and we use this principle. We do a lot of exercise, right? So it's more like it's just for a single point. It for a single particle, it's quite easy. It's just another expression of second law of Newton's. So here we have so this part dMV dt will equal F, right? Will equal F. So this part actually is just the same as R cross product sigma F, right? And then we should look the second part, dr dt, because dr dt actually is V. When we do the cross product MV, so you can find actually this vector direction is the same for this vector direction. It's just skewed a little bit with value m. So that means the two vectors of this cross product, its intersect angle is 0. So this part will be 0. That means the whole part of this will be 0. So then we will have this. We will have this dMOMV dt just equal R cross product sigma F. And this is the reluctant force of this particle acting on this particle, actually in the moment of this reluctant force to the same point. So this is the principle of angular momentum for a particle, right? It's just it's more like this. If we have, I think we have this R cross product sigma F, because our dMOMV dt just equal this, just equal this one, and this part is 0. So just equal R cross product dMV dt, and dMV dt actually is MA, which the same thing sigma F. So it changed into R cross product sigma F. And this one actually is all the forces acting on the same particle. Its reluctant force F, its moment to the same point O. So that is principle of angular momentum for a particle. It's just deduced from the second law of Newton's, right? So this one will very important for us to understand. So maybe we should give a highlight this. So therefore, we have dmo mvdt equal MOF. So this principle tells us that the moment about the fixed point of all the forces acting on the particle equals the time differential of the angular momentum about point O. So what this principle will let me put it this way. Can you guys think about its application? So how can we use this expression to do something for us? So if we have mv and we can do the calculation dmv dt, maybe we can find some MOF, right? So maybe we can use this principle to do some calculation. So let's try to see the paragraph together. This relation, particularly when extended to a system of particles, it is the start for a single particle, but our final destination is extended this principle into a system of particles, right? So under condition, I'll provide one of the most powerful tools of analysis in dynamics. So our final destination is to do the dynamic analysis for a body system, right? A body system. We should find the relationship of all the external forces, all the external moments, its relationship between all this load and all the kinematic information of the whole system, right? So it is widely known as the principle of angular momentum for a particle. But our final definition will just use this principle of angular momentum for a single particle to extend it into a system of particles. And this equation, we can do the projection. Then we will have three scalar components, just like what we have learned, principle of momentum from chapter 12, right? So we have dmx mv dt. So once again, you guys, you should turn to your textbook to page 224. There's some printing errors here and here. So it should not be dv. It always should be dt, right? So dmx mv dt will equal sigma mxf. That means all the let me see, reluctant force is moment to axis x will just equal to dmx mv dt. That is equals the time differential of the angular momentum its component along x-axis. So for the same reason, we have dmy mv dt equals sigma myf. And dmz mvdt equals sigma mvf. I hope you guys can understand this. Actually, we just talked about two things. One is the concept. What is angular momentum of a particle? The second is we just give you guys a proof, talk about how we can find this principle of angular momentum for a particle. Actually, we just do a time differential calculation, and we also use this second law of Newton's, and then we have a very useful conclusion, right? And let's say, so we have equation 13 to 5 and equation 13 to 6. And no new basic information since they are mere alternative forms of Newton's second law. I just call second law of Newton's. It's the same thing. Actually, for a single particle, it's no use to this, right? Actually, it's just another expression of second law of Newton's. But, you know, our final destination is extend this principle to a system of particles. So that's the very important aspect. That's why we have learned this from a single particle first. Later, we will talk about how to use this principle to a system of particles. Then we will use that conclusion to do some exercises, right? So let's continue to talk about conservation of angular momentum. So in Chinese, maybe I can give you guesses. Meaning in Chinese means 动量矩. Because we Chinese call angular momentum with 动量矩 or 角动量. Conservation means 守恒. So we have discussed the same thing from the principle of momentum from chapter 12. No? So if the moment of all forces acting on the particle about a fixed point O is 0, no? That means what? From this equation, if we know dMO dt equals sigma MOF, but if we know MOF is 0, that means this dMO dt must be 0. That means MOM will be constant vector, right? So it will be a constant vector. That means its magnitude and direction will never change at different time moment, right? So almost the same, from what we have learned from chapter 12. So maybe I can give you a guess, because our principle of momentum is dp dt, right? We have dp dt equal sigma f. So if we know sigma f is 0, that means dp dt have to be 0. That means p will also is what? Is a constant vector, right? More like this. A constant vector will never change its direction and never change its magnitude. So if we cannot have this condition totally fulfilled, but we can find if some component like mxf equals 0, myf equals 0, or mzf equals 0, then we will have this mxmv will be constant vector, my will be constant vector, and mz will be constant vector respectively, just because we also have these three equations, these three scalar component equations, right? So if this one is 0, that means mx will be constant vector. If this one is 0, then it means this one will be a constant vector. So that all tell us the conservation of angular momentum. In Chinese, we call that 动量矩守恒定律. 守恒 means never change, because it is a constant vector. Its direction and its magnitude never change. That means conservation. So we have this equation 13 to 7 and equation 13 to 8. And these two equations are known as the principle of conservation of angle. Actually, 角动量守恒或者质点动量矩守恒定律. You know, the principle of conservation of angular momentum. If only one component of a moment vanished, so that means one component of vanish means it is 0, right? It is 0. more like if mx f equals 0, some one opponent of this is 0, then only the corresponding component of the angular momentum is conserved, 是守恒的 conserved, will keep its original value, will never change along this axis of this component, right? So angular momentum may be conserved about one axis, but not about another axis. So a careful examination of the free body diagram of the particle will disclose whether the moment of the resultant force on the particle about the fixed point is 0, in which case the angular momentum about that point is unchanged. So that's all the knowledge point of the first section. Then we'll try to understand a typical example. So I hope you guys can totally understand from this class. So let's see, we have a sample example 13 to 1. So you guys can just looking at this picture, I will reading the paragraph. So we have a circular table here. No, we can find from this. So it's rotating at a constant angular speed, omega equal 20 radians per second. So this is the rotating table about the vertical axis, z axis. So this is the axis. So we have a block B with mass m is placed on the table with 0 initial velocity. You know, so we just let this from rest state on the table with the string AB taut. So we have a very thin string AB, which is tied on A. This is Z axis, and on B. So when we finish this action, the block sleeps for 4 seconds. Remember this value before reaching the speed of the table. That means after 4 seconds, it just rotate along with this table around the same axis Z. So after all this known, it let us determine the coefficient of kinetic friction between the block and the table. So what did that mean? Because it will from when we place this block from 0 initial velocity on the surface of this table, it will change its position until move into here. And this AB will change into a straight line, and R will be 0.5. And actually, the whole preset, it will have kinetic friction, 滑动摩擦, not static friction. So maybe I can tell you guys when we have learned something, because if we have a wheel like this, very ugly. I'm not good at draw something, right? So if we have a wheel and here it mass of center, we have V0 and A0. That's what we have learned. And this is the center of mass. If we see actually this wheel is a typical plane motion of a rigid body. So if it is a plane motion, and if we see this is a pure roller, 纯滚动, you guys still remember pure roller. That means there have no relative movement between this contact, because this contact will have 2 points. One point is on the wheel, another is on the ground. The 2 point contact at this time position and this time moment but these 2 points will have zero relative movement. So that means here we have, that means 2 things. One is we have a static friction. The second is this point we can call that an instantaneous instantaneous velocity of instantaneous center of velocities. So that means our V0 will equal omega times r. Let's say this r is the radius of this wheel. And then we do the derivative calculation, both sides of this expression. We will have alpha v0 its derivative will be a0, its acceleration along the horizontal line, right? And this one will be alpha, means angular acceleration times r. So this is very important thing that we have learned. So I do a quick review, and I hope you guys can understand it a little bit more. So that it means it will have a static friction, and here we also means this contact point will be instantaneous center of velocity, 顺心, right? So we can find if all these conditions fulfilled, then omega must along the CW direction. Maybe we give the same assumption of alpha, angular acceleration alpha, right? So maybe later we will do some exercise, we will do some example, maybe we also use the conclusion. So back to this problem, back to this problem. So it means let us determine the kinetic friction between the block and the table. How can we finish this task? So let's say the analysis. So we can find this, actually just we select this block B as an object to be studied. We should give it a false analysis. You see? So because this block is placed on the table, which have a constant angular speed omega equal 20 radians per second, right? So along the vertical direction, we will have its own weight, and a support force Fn along the same direction, because it's not jump upward and downward on the table. It's always stay on the surface of this table. So in this direction, it will have zero acceleration. Then along the AB direction, because we have the string, we have to learn 5 common types of constraint. This string is a typical one. We have a conclusion that this kind of string always pull the object, never push. So if you just try to consider the action from this string to this block B, it will have a Ft. Here T means tension. T means tension, 拉力, right? Tension. Another is F equal mu K times N, means here actually F will equal mu K. Not N, I think it should be F1. It should be F1. It's a normal pressure between the block and the table, right? That's the whole force analysis of block B. And then we can find the free body diagram of block B is shown in this figure. And the tension Ft in the string passes through the z-axis, So this action line Ft will have a intersect point with z-axis. That means this force will never have a moment to the axis z, right? And you guys can find W equal mg and Fn. These two gas direction is parallel to z-axis. So these two forces only also have zero moment to axis Z, right? So the tension Ft in the string passes through the Z axis, whereas the weight W and the normal contact force Fn are parallel to the axis. Hence, the moment of each of these forces about the Z axis will be zero. So this one, and this one all will have no moment to the axis Z. So the moment of kinetic friction force F, because its direction is along this direction, right? So if we use A at the center, we use R at the radius, then we can draw a circle on this table. Actually, this F will tangent to the circle at point B. You guys understand what I'm talking about? So we will have mz. So this force is moment to z axis. It's very easy to calculate because this direction and this direction will perpendicular to each other. So their distance from this one to this one is just r. So what our mz is mu k n r, right? Mu k n here n we also can write as fn, and we can easily find actually fn equal mg because of this direction never had any acceleration. So after all this, we will applying the principle of angular moment about z axis, right? So dmz dt will be sigma mzf, right? So our dmv dt, our dmv, m here v is what? V is omega times r, right? Omega times r. So we have d mv. Omega r is v. Mv is its distance from A to B, from this line to this axis, actually is another r. So we have dmr squared omega dt. So mr squared alpha. So here is the thing. What is alpha? Alpha means it's from 0 to 20 radians per second. It's just use 4 seconds. So we have alpha equal 20 over 4, which is 5 radians per second squared. Then we replace this alpha with 5. Use this. Then we use this mu k fnr. And you know, actually Fn equal mg, then you can very easily find the final result, mu k, which is the kinetic friction coefficient. The coefficient of kinetic friction between the block and the table will be this, right? Will be this because of this expression. Because this one will equal to this one, right? Because Fn equal mg, so we can eliminate m. Then we will find mu k will equal r alpha over g. You can use 10 to denote g, or you can use 9.8 to denote g. It's the gravitational acceleration of the Earth, right? So you can find the final result is 0.2555. So I think that's all for the first section. I hope you guys can understand a little bit. Maybe we should have a short break. We will restart today's class at 11:10. So all you guys please have a short break. See you later. Okay, everybody, our time is up. Let's finish today's second class. Actually, we have finished the first section learning. So back to the beginning of the first section, we have talked about what is angular momentum. That is the concept of angular momentum. It's a new thing for you guys. So I think it's more it's very good for us to compare to understand the moment force for a force in space is moment to a point O. So since F is a vector, you can think about that moment, linear momentum, P equal mv is another vector, right? It also can have some kind of moment to the same O because it have the similar expression MOMV equal R cross product MV. So after we have this concept of angular momentum of particle, then we find its principle. By what? By we do the differential calculation. When we do this differential calculation, we found that because this part will be 0, and this part is just the reluctant force acting on the same particle, its moment to point O. Actually, I think the essence, the 本质 essence, the importance of this principle is it give us a method to link its kinematic information, because here velocity is a kind of information of movement, right? And the force of moment. So it's more like the second law of Newton's. We have another method to find the relationship between mv and the moment f, right? So that is the very important aspect of this principle of angular momentum for a particle. So we have this vector equation, we have the three components of the scalar equation, so we can use this. The third one, the final of this, the first section, we talk about the conservation of angular momentum. I think this part is very easy to understand. It's just from the mathematical point of the mathematical knowledge points. So if this one equals 0, then dp dt equals 0. The same is MOMV equals 0. So we have the so-called the principle of conservation of angular momentum. And then we have an example. So this class will try to move to the second section. We are trying to talk about principle of angular momentum for rigid body. See, actually we have a clue. The important aspect is we will extend, you remember we have this, we will extend the principle of angular momentum for particle to a system of particles. So here the second section talk about principle of angular momentum for rigid body. So actually we can think about that. It is true. Actually, rigid body is a system, a kind of system of particles. A system is hard to write. A system of particles, right? So we can think about that. There are a lot of particles which constitute the whole body, but because this rigid body is ideal a model of forces because it never change its shape, it never have any deformation, no matter how big load acting on this body. So every two particles on the body will never change their distance. Particles. And our final definition will be body system. So first, we are going to talk about the principle of angular momentum for rigid body. So let's see. So I think when I read the paragraph, maybe it will help you guys have a best understanding of the concept of principle. So if I just use this very short PPT, maybe it's harder for you guys to understand, right? Maybe it's harder for you guys to understand. So here, the second, we just talk about the principle of angular momentum for rigid body, right? For rigid body. So we're back to this again. So please, you guys try to follow me, try to pay attention to what I'm talking about. The plane motion of a rigid body can be specified by the motion of mass center and the rotation around the center point. Can you guys understand the first sentence of this paragraph? It has the plane motion of rigid body. So maybe we have a plane rigid body. Let's have the name A, right? So if we know actually this point C is actually it's mass of center, then we always treat the plane motion as it have two components of independent motion. One is translation movement along the mass of center C. Another motion component is rotation around point C. So that's the whole sentence meaning. The plane motion of a rigid body can be specified by the motion of the mass center, here is the center C, and the rotation around the center point. The two force equations of translation have defined the motion of center. So can you guys understand the meaning of the first half of this sentence? The two force equations of translation have defined the motion of center. That means actually what we have learned, MAX. So we can clearly write that MACX equal sigma Fx, right? So we also have MACY equal sigma Fy. So here, the two force equations means these two equations, right? We have learned this, we call that in Chinese the 质心运动定理, the principle of motion of the mass center. So MACX equal sigma Fx, and MACY equal sigma Fy. So let me put another way, try to help you guys to understand this. So let's say if there are a lot of loads acting on the body A, if we select the point C as the point to try to simplify all the forces onto this point, we will have a principal force. We call that 主使. We also have a principal moment MC, right? We can think if Fr is not zero, we can think actually we have MAC, right? Means the mass of center is acceleration AC will equal Fr. And this is the vector equation. It can be projected into two components because plane motion we just consider x direction and y direction. So that is the two force equations of translation have defined the motion of the center. And an additional equation is required to specify the state of rotation of the body. You know, that means we still require another equation to give us the information of this rotation. That means that the rotation movement is the relationship between the movement and the moment MC, right? Therefore, two force equations and one moment equation are required to determine the state of rigid plane motion. Actually, that's why we should learn principle of angular momentum. Because through this principle, we can give another equation, specify the state of rotation of the body, right? That's the reason why we learn today the principle of angular momentum. So please, you guys try to follow me and try to understand how the paragraph's meaning. So in the kinetics of rigid body, plane motion, which have angular motion, right? I think rotation and translation is totally two independent movements. So actually we can, because it's independent from one to each other, so we can use the so-called let me say, in Chinese we call that 运动叠加原理, and in Chinese maybe it's motion superposition. So let me explain to you guys. Later we will use this principle. So if we have two independent motion components happening at the same time, so we know these two motion components happened at the same time, but we deliberately treated as actually the two motions happened from one to each other, because it will have the same result, right? It have the same result. It's more like when we treat a plane motion of a rigid body, because when a rigid body have plane motion, it will move along the center of mass C and rotate around the C. All the two motion components happened together. It happened simultaneous. So it's very complicated for us to study that. So we arbitrarily or we deliberately think actually it happened in sequence. So we can treat that the rotation part happened first, then the translation part happened next. Or we can think about the translation happened first and the rotation happened next. And the result will be the same. And then if we treat the two independent motion happened independently, one after another, then you guys will find actually the motion started very easy to finish. That's the motion superposition. In Chinese, we have another, maybe I can write here, 运动叠加原理. I think it means the principle of motion superposition. Motion superposition. So this is the principle of superposition will always use. It's very useful. It helps us to change complicated things into very easily understanding things. So 1 plus 1. So please, you guys remember the principle of superposition. So here we have another character in motion the superposition. The principle of motion superposition. So let's continue to find the second paragraph. Then we have to do a jump. You know why we have to do a jump? Look at the second paragraph first. So it tells in the kinetics of rigid body plane motion, which have angular motion, we must introduce a property of the body which accounts for the radial distribution of its mass with respect to the particular axis of rotation normal to the plane of motion. See, we need another property. So we must introduce a property of body, which accounts for the radial distribution of its mass with respect to the particular axis of rotation normal to the plane motion. So the property is known as the mass moment of inertia. In China, we call that 转动惯量. It's more like mass of a body because we have second law of Newton's F equal ma, right? So you can think about actual mass will determine the A because A will equal F over mass, M, right? It's another very important property where we are going to introduce to you guys is the mass moment inertia. Mass moment inertia is a new concept for you guys. Maybe you that mass moment of inertia from maybe physics, maybe not. And it is essential that we can calculate this property in order to solve rotation momentum. That means in order to solve the rotation problem, we should have the ability to calculate some common shape of this property. And the final sentence is very interesting. We assume that you are familiar with the calculation of mass moment of inertia. So I have the question. Do you guys know how to do the calculation of mass moment of inertia? Can some guy replies to me? Do you guys know the concept of mass moment of inertia? Until today's class, do you guys have the name of this? Do you know its meaning? The mass moment of inertia. Can anyone replies to me? Is there anybody still follow me, still listen to me? No?
Yes, Lord.
Thank you. Thank you for your reply. Do you know the mass moment of inertia before today's class?
No.
Yes, I think the answer is no. So first, we don't know this concept. Second, we don't familiar with how to calculate this thing, right? So that's why we have to do a jump from here to what? To chapter 11. No, to chapter 11. Actually, you guys come back to your textbook. You can read the second section of chapter 11. Actually, when we after the learning of first three sections of chapter 13, we'll back to here to learn this chapter 11. So you guys will know that the final chapter maybe of our this semester's learning is this chapter 11. We'll talk about the principle of work and kinetic energy. So here we should first learn what is. So first, I will introduce to you guys what is the mass moment of inertia. So please, all you guys, please try to follow me. If you still confusing what I'm talking about, please, you take your time, you back to here, you read by yourself. Okay? So, what is mass moment of inertia? Once again, I will give you its Chinese name. We call that 转动惯量. So here, 转动 means rotation. So it has some relationship between rotation and the mass moment of inertia. So in this section, we introduce the mass moment of inertia of a body about an axis. So first, let's know this concept. You guys can look at this picture 11 to 11. Shows the body of mass m. Let's say this body is shaped more like a potato, right? Have mass m. That occupies the region V. V maybe its value, right? So we know mass m equals rho times V, and rho is then density 密度 right v is volume 体积 so in Chinese we have this equation I can write it to you guys 质量 equal 体积乘以密度 so it's more like this mass equal volume v times density. Am I right? I hope this maybe it's not incorrect for density. So that is this volume density because it maybe it's not correct. So I will delete it here. Okay. Okay. So R is the perpendicular distance from Z axis to the differential mass dm. You know, so you guys please try to follow me, try to listen to me. So if we arbitrarily select a very, very small part of from this body, so let's say it has a mass dm, because it's very small and small enough, just like a point. So this point will have a distance to its rotation axis z. So let's say this distance is r, right? Is r. So after we give all these things, the mass moment of inertia of the body about the z-axis is defined as gz. You know, we always use g, gz means it's around the z-axis, equal integral calculation r squared dm. I don't know if you guys can understand this. Actually, it will equal integral calculation actually equal maybe we have a lot of part from 1 to ultimate. A lot of numbers are ri squared dmi. It's more like this. It's more like this. So maybe in some time we also can write as this. It's just equal. It's just equal this sigma ri, because I means number s mass component of the whole body mi. So this number can be unlimited, unlimited. How you guys read this? Simple. Unlimited. Infinity, right? It should be infinity. 无穷大 in Chinese with 无穷大. You can think of any number and this guy will greater than your number. You just pick out, right? 无穷大. So it will be seen shortly that this integral is the measure of the ability of the body to resist a change in its angular motion about the axis. So if we try to study the relationship between the rotation and the moment, we should first know this mass moment of inertia. So believe you guys, it's a very important property for a body. It's just according to its mass distribution. So you know, so let's see. Just as the mass of a body is the measure of its ability to resist a change in its translational motion. So we can replace with this the moment of the mass moment of inertia is a property of the body. It is a measure of its ability to resist a change in its rotational motion. You know? So maybe I will repeat. Just as the mass of the body is a measure of its ability to resist a change in its translational motion, our mass moment inertia is a measure of the ability of the body to resist a change in its angular motion about the axis. Why? Maybe I can tell you first. Actually, we will have this kind of relationship if we use GZ to denote this so-called mass moment of inertia of this body to this. It times its angular acceleration alpha will equal mvf. No? So you guess this actually is the relationship between moment of outer forces to the axis Z and the rotation around Z, because alpha is rotational angular acceleration. So it's more like what we have learned, second law of Newton's, ma equal F. You see? So that's why we said that mass m is a measure of its ability to resist a change in its translational motion. So you can find the bigger m is, the smaller a will be if the f is the same value. So that's why m is the measure of its ability to resist a change in its translational motion. So you can think about one thing. If there are very, very huge metal ball, you try to push to change its translational motion. So because it's big enough to you, you can never change its position, because the bigger m is, the higher ability of it to resist a change in translational motion will be. See? Can you guys understand me? So the same thing is, the higher the GZ is, the change of alpha will harder to be, right? So this GZ will tell us its ability to resist a change in its angular motion about the axis. That's why we have learned the mass moment of inertia. I hope you guys still follow me, because this concept is very important. I hope after this semester's learning, you will have something left. That teacher Fang has told us what is the mass moment of inertia, and some common shape of body we know how to calculate its mass moment of inertia. Please, it's more very important, just like m, because all of us know what is m. It's a mass of body. And GZ actually is mass moment of inertia. So please follow me. From its definition, we see that mass moment of inertia, it's very hard to use in English. We should use 1, 2, 3, 4 words to give it meaning. But in China, we will use 转动,惯量. So it's more convenient for me in Chinese, but it's hard for you guys to understand, right? So you can try your best to try to learn Chinese. I hope I can teach you guys in Chinese. Then it will be very easy for me. So we see that mass moment of inertia is a positive quantity. It's a positive quantity because here are squared, so it will never be negative, and this m will always be positive. So the mass moment of inertia is a positive quantity with the dimension m meters, right? M will be mass kilometers, L is meters squared. In SI units, 国际单位制 GZ measured kilometer times meter squared. Then we will have another concept. This is not very important, but you should know the radius of gyration. This 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 word is very strange to me. Gyration. Am I correct to give this pronunciation? Gyration. So we have rho in molecular density, you know. So if the radius of in Chinese, I very familiar is Chinese name. We call that 惯性半径, you know, it's 惯性半径. So if we know somebody's gyration rho, that means it's mass of inertia, mass moment of inertia, MMI, mass moment of inertia, that its G will just equal M times rho squared, more like this part, M R squared, right? Then actually rho will equal square root of GZ over M. Although the unit of radius of gyration is length, it is not a distance that can be measured physically. You know, it's not a distance that can be measured physically. Instead, its value can be found only by computation using 11 to 18. You know, so if we know GZ first, and we know the mass of the body, so we can just use this expression to find the rho. It cannot be measured directly or measured physically. So the radius gyration allows us to compare the rotational resistance of a body that have the same mass. So you can see the bigger the GZ is, the bigger the rho will be. That means the high ability of this body to resist is change of translational motion. And the third is the parallel axis theorem. Please, you get this is very, very important. So it tells us consider the two parallel axes. Please, you guys see this picture. We have this figure 11 to 12. The location of the axis is arbitrary. So we have two z's, one z prime, another is z. It have the same orientation. That means z prime will parallel to z. So the parallel axis theorem tells us if these two parallel the axis z prime and z have a distance d, then we have a very important relationship between gz and gz prime. You know, we have gz and gz prime. You see, please, there another condition you should, because the other axis which passes through mass center C, you know, so this z prime actually it is the special axis. The speciality is this axis actually through the mass center. No? So we have a very important relationship we call that the parallel axis theorem. Any arbitrary axis d, which is just parallel to z prime, but it has a distance from z prime, then we'll always have these expressions is true. Gz will equal gcz prime plus md squared. So we do not give the proof here that. I just need you guys to remember this. Maybe I can give you some application of this distance. Let me see. So actually we know homogeneous long thin bar. Let's say it has a length with L and its mass is M, right? So this time if I change the color, so it will have its center of mass C here, which at the half length location. right? So if we think about two mass moment of inertia relative to two axes, one is this, one end of it. So here, let's say this is GZ. Another is GZC. GZC. So the two green axes means one is through its mass center C, another is just through one end of this long rod. So I will tell you guys, actually we know first if this GZ its magnitude, maybe I should change it. GZ will just equal 1/3 M L squared. And the GZC, please remember these two things you should remember, will just equal 1/12. How to read this in English? 1/12 is the very, ordinary way. Can you guys tell me how to read this in a very clever, smart way? 1/12 ml squared. So in GC, so we can check the so-called parallelism theorem. So we can find actually the distance between these two axes will be FL, right? So from this expression, we should just use GCD plus M FL squared. It's result of it. So let us try M. So because L squared will be L squared over 4, right? So we plus 1 and we L squared into 3 squared over, then we can do this plus calculation. This one, that means JJ just use this parallel theorem equal 1/12 m squared plus can be read as 3/12 m squared. Right? So you can find 1 plus 3 will be 4/12 and can be simplified in third ml squared. So up we find this is very important from tell you only need to know a body is moment of inertia about an axis which is through its mass center, right? Then you can parallel theorem to calculate any arbitrary axis at long edge. This axis, this new axis is parallel to ZC, right? So that's the mass moment inertia. Hopefully you get with me together. Just look at this table 11-1. Tell us mass moment of inertia of homogeneous bodies. Homogeneous means it's 均匀的，均匀物质。Maybe it means at each part it have the same density, have the same density. So please, you guess there's something you should remember. So homogeneous bodies, just more like the bar I just draw here. So if we have a homogeneous bodies, and we call that slender rod, which is thin now. So actually, we can build a coordinate system. We have x-axis, y-axis, and z-axis. So actually, we draw here is more like we talk about its mass moment in about x-axis or y-axis. It's the same. So we have this C is centimeter. So this axis zero is let's say ml square. So just like this. So I remember this. I hope you guys can remember this. And if you just draw the axis, let me see. Let's see if we let me see x prime, x prime. So you will find actually this just will calculate this mass moment inertia about this x prime, which is parallel to x. So this one will be 1/3 ml squared. If we do this, we draw axis z like this, its gc is 0 because it is symmetrical, right? It's symmetrical. And this, we call that cylinder is not a slender rod. It's very fat rod, right? This is very slender. This is very fat. So it's fat enough, so we cannot ignore its radius. So it has radius r. Then its mass will be pi r squared h rho. Rho means density. So please, you guys have an impression here. We have x, y, z, and gx and gy will just e. This one very hard to remember. You only need to have an impression is enough. But this one you should remember because they, so if you look the cylinder from this direction, from the positive direction to the negative direction, you will find maybe this. You guys, and really or G. Then we have O, which this meson and GO will also have and are there. I hope that you remember. Donut. Do you know donut? It kind of bread, right? So here, all this internal circle is empty. That means all the mass are distributed to this part. So if we have its outer radius is r, its mass is m. So this donut in Chinese we call that 圆环. I don't know how to use it correctly in English. 圆环. Then it's let's say this point is O. So the axis through this O perpendicular to this plane figure is GO, please remember it will be mr squared without this half, without this. So if this is the disk, it's homogeneous. All the mass distributed from center to the brain. But these do not. All the mass are distributed along the brim of this circle. So its GO will be mr squared. So please, you guys, you'd better remember these things. I require you guys to remember. Right? Let's see. This is the homogeneous bodies, thin ring. So I think donut is thin ring, 圆环, a cross-section area. So it's GXGZ, GXGZ. So the GZ is very important. DX is dy. We do not use these two things very often. We use these two guys seldom use them. And we have sphere. No, sphere is the ball. Now we are watching a famous World Cup. So I look some guys, 朋友圈 said, I don't know the meaning, but I think it great Argentina, right? Because Argentina have win the third game again, right? So this is the sphere. So for sphere, Gx, Gy, Gz, because it is symmetrical, all will be half over 5m squared. But it's not very common. It's not very often used. So I do not need you guys to remember that. But this guy, this guy, this guy, this, and this, I hope you guys can remember. Because we will always use this term to do our axis, to tackle some problems, right? So the final thing is we have a homogeneous body. The shape is a rectangular prism, 长方体. I think Chinese name will be 长方体. 长方体. And this thin circular plate, just a disk. 圆盘. See? So for this 圆盘, this part is very important. No? For 圆盘, this part is very important because we have axis. Here should not be Z. There's some mistake. The X here should be Y. So our GZ will through C perpendicular to this plane, GC will be half mr squared, just like I draw here. So this one you should pay attention to, you should remember. And this one, you only need to have impression is enough. So if we have a homogeneous body which have a rectangular prism, maybe it has it have what? It have A along X, B along Y, and C along Z. So its volume will be what? ABC, right? It will be ABC. So let's see this volume. So rho is density. So density times V will be mass. And you see Gx equals this, Gy equals this, and Gz equals this. It's very hard to remember, so we will not need to. I think that's all for today, and we don't have homework today. So I hope you guys maybe you still have some confusing, cannot understand what I'm talking about. Please back to our textbook and read it by yourself, especially this section, second section of 11, chapter 11, talk about mass moment of inertia. Next time we will use some information we have learned today to do some examples. So I think that's all for today. Bye bye, you guys. 那今天就到这里吧，好不好？下课吧。再见，同学们。 还有人在听吗？OK OK，拜拜拜拜，
OK，老师，再
拜。
见
再见再
，Thank
见
you。
，Thank you。